Physics and techniques of magnetic resonance imaging. The image on the left is a cartoon of protons being aligned with the main magnetic field called B0. The ones which are aligned are marked with stars. Now this is a great exaggeration because the actual alignment in real terms at body temperature is only about 1 in every 100,000 protons. Why is this so small? It's because the alignment force generated by the presence of the magnetic field is actually quite tiny compared to the randomizing force of the thermal background, in other words, the body temperature. If we chilled the patient down near absolute zero, we could get nearly all of the protons to align, but obviously this is not practical here. When we take all those aligned nuclei together, they become M0, and we see that with the red arrows, they actually do not align exactly along the magnetic field, but at a slight angle. The protons align along the main magnetic field because each proton is a spinning sphere of charge. So each little proton has its own magnetic field. Just like two bar magnets, they tend to align along with each other. So this tiny but very slight tendency to align is actually not exactly along B0, but at a slight angle. So the nutation process is the spinning of the proton itself, and the precession is the motion of that spinning vector around the main magnetic field in a process we call precession. Precession leads to a phenomenon called the Lamor frequency, and that is the frequency with which these spins proceed around B0, and that frequency is a linear function of the main magnetic field and the intrinsic strength of the magnetic field of each proton. This is where we get the concept of resonance in magnetic resonance imaging. When you communicate with these spins, you have to do so at their resonant frequency, and this is called the Lamor frequency. The Lamor frequency is a direct linear function of the main magnetic field and the strength of each magnetic field of the individual proton. The Lamor frequency is given by the simple relation of main magnetic field times the gyromagnetic ratio of the nucleus itself, which will give us the frequency of resonance. So at 1.5 Tesla, if we're looking at the hydrogens in water, that precession frequency is 63.86 million cycles per second, or 63.86 megahertz. Now that's a very interesting phenomenon, but it doesn't really do us any good, because if we stick a sample in a magnet, it will just sit there and we won't be able to get any information out of it. So in the image on the right, you see spins in a magnet, and so in a magnet we consider these spins all to be simply aligned along a particular direction. So spins at rest, as you see in the image on the right, taken together we call M0, or that is the longitudinal rest magnetization at equilibrium. That, again, that's an interesting phenomenon, but it really doesn't do any good for us. So how do we connect? How do we communicate with these spins? Well, we have to turn them into the transverse plane with another magnetic field called B1. So we made B0 by building a large magnet. So how do we make B1? Well, we make B1 with a radio frequency transmitter, as you see in the image on the right. And that radio frequency transmitter and receiver connect to a radio frequency coil, which is also more commonly known as an antenna. So we literally are transmitting into the sample with the transmit antenna, and then a moment later we will receive the signal from the sample with the same coil or a coil like it. Here is a schematic diagram of the parts which accompany the radio frequency coil. We have to have a large RF signal in, and this can be from relatively low power like 50 watts up to very high powers of 20,000 watts plus. Now that is a lot of power, but we transmit it in very short bursts, and the machine is monitored very carefully so as to not overexpose the patient to radio frequency power. It's a huge amount of signal that we put into the patient in order to create the B1 magnetization, which tips M0 into the transverse plane. Now we turn that signal off and then we listen. And the signal that comes out of the patient or the sample is extraordinarily tiny. And that we put through a preamplifier, which is the triangle that's pointed in the right direction, and then into a receiver, and that is where we create the signal from which we make the image. Having had the magnetization created by B0 and then turning it into the transverse plane, into the XY plane, with another magnetic field which we call B1, which we created using a radio frequency transmitting antenna. We turn off that transmitter, and now we have a signal coming back. What are we going to do with it? Well, there's a couple of things. One is there's a very important fact that this frequency of this signal is going to be exactly determined by the Lamore frequency equation, and that is only dependent on the magnetic field right at the point of that particular spin. So we can use a gradient magnetic field. In other words, we can modify B0 in a linear fashion in any direction, and that will tell us the position of the spin, because as we increase the magnetic field with the gradient, the frequency of resonance of that spin will go up too. Or if we decrease it on the other end of the gradient, it will go down. And so much like the keys on the piano, we can tell where that spin is by the frequency that it creates. Here's a cartoon of a gradient field. And what we see is this is a gradient field that we've created in the X direction. And as we go further away from the origin, or from zero in the X, along the X-axis, we see that the magnetic field increases to the right and decreases to the left. And so the frequency of resonance of that spin will change exactly as a function of the distance away from the origin. The gradient allows us to combine the spatial localization, in other words, knowing where the spins are, with the ability to create a B1 field just in a single slab through the patient. In this illustration here, we see a patient with 4 slices in the axial plane, which were created by 4 radio frequency pulses, also known as B1 pulses, but in different locations along the Z-axis. And this is because we can use the gradient to change the frequency of the resonance of the spins in the patient. One of the most important things about MRI, as opposed to something like CT or conventional X-ray image, is that we can inquire about soft tissues and their structures by looking at different components of the MRI signal that we receive back from the patient. In this image, we see 3 different types of tissue and their so-called T1 relaxation of each type. Now, this is a function of how these protons communicate with the background protons in the object itself. So, for example, in CSF, the water protons in CSF communicate very poorly with the background, and so the relaxation times are very long. So once we've excited the spin into the transverse plane, which is shown in the far left three-dimensional axis, everything is excited and there's no longitudinal relaxation going on at all. As time goes on, there is continued longitudinal relaxation back. Eventually, if we let this go long enough, everything will have relaxed all the way back to M0, or what we call MZ equals 1. But the rate at which these relax is all a function of the water and the fat protons in the particular tissues. And so we see those are different, and using this we can actually create contrast between different types of tissues. Another type of relaxation process that we can detect in the tissues of the body is called T2 star relaxation. So remember, when we put the person into the magnet, what we generated was M0, which was a magnetization along B0, and then we tipped it into the transverse plane as shown here by a radio frequency system, which is not shown here. If we wait some period of time, those spins in the transverse plane will all go slightly faster or slightly slower than the others, even without the influence of the gradient. And so what happens over a long enough period of time is we can see that the amount of signal that these generate continues to drop to zero. They all will drop to zero if we wait long enough, but they will drop to zero at a different rate dependent on what is the material itself. What are these protons communicating with? The third category of relaxation is, as opposed to T2 star, is T2 relaxation. And here's an image of how the T2 relaxation process works. And we use a pulse sequence called a spin echo sequence to do this. So in the upper left-hand corner, you see the RF90 pulse. The B1 pulse has twisted M0 down into the transverse plane. And in part B of this figure, we see the spins losing coherence. In other words, some are going faster and some are going slower, just as they did in the case of T2 star relaxation. But then in part C, sub-image C, we've put another larger B1 pulse in called a 180-degree pulse. And what that does is changes the direction in which the spins are moving. And at the time of the echo itself, which is subpart D of this image, the spins all come back together. Now, they don't all come back together, and what we get as a result is similar to the T2 star relaxation, but is yet another transverse relaxation component called T2. The timings in the pulse sequences, in other words, when do we play the various RF pulses, and when do we receive the signal, and how often do we repeat those pulses, are the things called TR time, in other words, repetition time. That's how often we repeat the sequence, and the time from when we actually excite the spins to when we go look for the signal coming back, that's called the echo time. One of the most important things you'll manipulate when you're setting up an MR imaging sequence or reading an MR imaging sequence is to understand the effect of the repetition time and the echo time. If we do a spin echo image, as we saw in the previous slide, we will pick a repetition time and an echo time. Now, the echo times are typically from maybe 5 milliseconds out to several hundred milliseconds, while the TR times are much longer, they're typically on the order of around a second, a fraction of a second to several seconds. So how do we pick what these numbers ought to be? Well, it depends on what kind of contrast weighting we want to create. So if we want what is called a T1 weighted image, we do a short repetition time, which may be a half second, and we would do a short echo time, which may be 20 milliseconds or 0.02 seconds. If we want a T2 weighted image, we would have a long repetition time, which might be 2 seconds, and a long echo time, which may be 100 milliseconds or 0.1 seconds. If we want a proton density weighted image, we would again use this long TR, but then go back to a echo time that was similar to what we would use with a T1 weighted image. And then there's a fourth place, long TE, short TR, that we would not use, and because that gives us mixed up contrast. One of the most important things in reading or prescribing MR imaging sequences is to attempt to purify the contrast. In other words, what we want is, in a T1 weighted image, we want the image to look, we want the image to change, the intensity of the things inside the image to change based only on their T1 relaxation time. And the same is true of T2. So knowing these things, it's very important to know this little four-corner box to understand what you want. Making an MR image requires that we repeat the sequence a number of times in order to get all of the data about the spatial frequencies in the image. And so to make a complete image can take from a few seconds to many minutes, and this can be a problem for some patients. In the 1980s, 1990s, a T2 weighted image would typically take on the order of 8 minutes to acquire. An 8-minute image is sometimes beyond the capability of a patient to remain still, and MR imaging is very much dependent on the patient remaining still, at least in conventional imaging. So one way to do this was to do something called fast spin echo imaging, and that is to acquire many of these different spatial frequencies all in a single excitation here. So we fill up, in order to do an image, we have to fill up a matrix called K-space, and in order to fill up K-space in a conventional image, we get one line of this matrix in every repetition. In fast spin echo imaging, we get multiple lines in a single repetition, as shown here. So this is a fast spin echo image with something called an echo train length of 4. So this goes 4 times faster than a conventional spin echo image series. And so what happens here is, instead of taking 8 minutes to make this image, we now get a substantially similar image in 2 minutes. 8 minutes divided by 4. There are many different kinds of pulse sequences which can be used to create different kinds of contrast depending on what particular pathologic state you're interested in seeing in the patient. In the inversion recovery sequence, we start by playing a much larger radio frequency pulse, an RF-180 pulse, and then we play a conventional spin echo 90-180. And what this does is turn the longitudinal magnetization all the way from +1 to -1, and now we have a much longer curve over which the T1 relaxation occurs. One of the convenient concepts within this idea is that we can image where a particular type of tissue is actually going back through zero. And when that longitudinal magnetization goes through zero and we play the spin echo sequence at that time, what you see in this image where the light purple or gray matter line is, you see it's going through zero, and in the resulting image it will disappear. So this is another way to null out particular tissues that you don't want to see. This is a practical experiment and illustration of that, which I did a number of years ago, using a patient volunteer and a jar of mayonnaise. So the patient was lying in a head coil, and I put a jar of mayonnaise just above his head. Mayonnaise is a fatty substance which has a T1 very much like the T1 relaxation time of human adipose tissue. And what we see is the different TI times. In other words, that is the time between the first RF-180 and the start of the spin echo sequence. And we see here repeated imaging at TI times of 50 milliseconds out to 600 milliseconds. And what you can see is that by choosing the appropriate inversion time or TI time, we can darken or brighten particular tissues. So at 250 milliseconds in this particular image, we see that the white matter in the patient's brain is completely darkened out. And in fact, at 500 milliseconds, the opposite is true, and the gray matter has darkened, and the white matter has highlighted. Now, if I wanted to get rid of the fat in the image, I would pick a TI time of 110 milliseconds, where you can see that the image of the mayonnaise has completely disappeared. This figure shows echoplanar imaging. In the top, we see the pulse sequence that is associated with echoplanar imaging. It's a readout gradient which reverses very quickly, and one radio frequency pulse. What this allows us to do is to take all of the data in K-space in a single excitation. So within a 20 millisecond window, we can take one complete image. And there is one of those complete images in the lower left-hand corner. You see it is very heavily T2 weighted. In other words, the CSF is bright. And then in the lower right image is the same slice, but acquired with a spin echo pulse sequence. One of the things that you'll notice is in the echoplanar imaging, especially in the bottom of the temporal lobes, you'll see that there is significant geometric distortion there. That is because echoplanar imaging is very susceptible to changes in the magnetic field, which happen, for example, in the base of the brain, because you have tissue next to air, and the magnetic field changes in intensity simply based on what tissue it's going through. That being said, this is incredibly useful pulse sequence for imaging things that happen at a very rapid rate, or for patients who cannot hold still. This figure illustrates something called perfusion imaging, and how perfusion imaging works is that we do echoplanar imaging of the brain, as shown in the box in the image marked A, and we have a radio frequency pulse just inferior to it. The radio frequency pulse nullifies the signal in the arterial spins, in other words, the blood that's flowing into the brain, and we compare that with another image that we make with the saturation pulse turned off. That gives us an image like we see on the far right, which we see colorized, where the color is a function of the actual flow of the spins into the brain. In the middle panel, panel B, we see the MR angiogram of this patient, and you can see that the patient's right middle cerebral artery has become occluded, and so we see it disappears in that image. But importantly, the perfusion image on the far right in panel C shows us that the brain is poorly perfused on that side, being not nearly as red or yellow there. This can be very helpful, especially in cases where the vascular defects are not nearly as obvious as they are in this case. perfusion imaging is useful not only in the case of poor perfusion, for example, in infarct, but also in areas or questions of hyperperfusion, such as in this neoplasm here where the highly perfused area is shown in bright red and yellow. Not only can we make images with the magnetic resonance process, but we can also extract spectra from tissues in the body without having to remove those tissues from the body. So if you remember organic chemistry lab and your identification of unknown compounds using a test tube and a large magnet, this is a very similar thing. But we use gradients in order to localize the tissues themselves. And in this case, we have a suspect lesion in a brain of a patient, and on the showing two voxels from this patient. On the left is the contralateral or normal tissue, and we don't get to see quite as much as we do with a high-resolution magnet and a test tube, but we get to see perhaps 20 metabolites from which we can draw quite a bit of information. So this is a normal-looking spectrum on the left from a normal voxel in the normal brain, and then in the right, this is a voxel taken from the lesion, and what we see here is a resonance called CHO or choline, and choline goes up in active neoplasms because active neoplasms are building membranes, and N-acetyl aspartate or NAA, which is normally the largest resonance, goes down because that is only found in living healthy neurons. So here the living healthy neurons are no longer living or healthy, and the membranes are being built in the neoplasm, and it's also starving for oxygen, and so the lactate resonances, there's two in this image, are going up. Magnetic resonance imaging also allows us another kind of functional data, which has become known as functional MRI. So if we take the echoplanar imaging, which we saw a couple of images back, and we repeat that over and over again while we have the patient doing some kind of a directed task in the magnet, we can detect the change of blood flow in the patient's brain in the locations which are active for that particular task. Why is this? Well, it's because, we get a slight change in the magnetic susceptibility of the tissue in the areas that are changing because of the differing ratios of oxy to deoxyhemoglobin in those vascular structures. Again, using echoplanar imaging, we can actually make an image whose intensity is dependent on how much the water is diffusing or moving on a microscopic level over the course of the imaging sequence. So echoplanar imaging allows us to do this quickly enough to actually see that change, which is typically on the order of less than a millimeter. And if we take that and we sensitize it in here in multiple different directions, we can actually see which way the water tends to diffuse. So if you imagine water in a very small drinking straw, the water will tend to diffuse along the length of the straw, but can't diffuse through the walls of the straw. Well, it's been discovered that we can use this to see where the water is diffusing, and by doing so, we can actually make images of white matter bundles where the water is diffusing along the direction of the axons in the bundle. So if we color code that, we wind up with an image like we see here. Now the arrow that points toward the black area, that's pointed into the CSF. And the CSF, the water in the CSF diffuses in all directions equally. So we get no color there. The top image, we see that the image is colored red, and that's a false color image, but it's because this is in the corpus callosum, and so these white matter bundles are oriented left to right, and so our left to right color in this false color image is red, so that turns red. And we can see, again, the green and the blue images, those are white matter bundles that, in the case of the blue image, are coming up in the X direction, and in the green, it's in the anterior to posterior direction. In this image, we've used the same diffusion tensor imaging as we saw in the previous image to get, in 3 dimensions, images of the white matter bundles in the brain. And there are several different ways to look at this data. So in panel B, this is essentially the same false color image encoding that we saw in the previous figure. And then on the left, we're simply measuring not the direction of the diffusion of the water, but simply the amount of the diffusion of the water. So in other words, it's a measure of anisotropy. In other words, how likely is the water to be going one direction rather than all 3 directions? And so the more likely it is to be going in one direction, whichever direction that is, we make that redder. And if it's more isotropic or in all directions, we make the color bluer. So that is an anisotropy map on the left. And then the far right, taking this data and going one step further on it, we can actually make images of these bundles as they travel through the brain. And so what you see in this patient who has a neoplasm on the right, you can see that the image of the white matter bundles is certainly obscured because the white matter has been by and large disrupted or destroyed on the patient's right.